large project with 23 partners running from June to 2022 until November 25, and has a budget of 18 million. And as I mentioned, this is going to be represented by Matteo Ranavoldo. Then we'll hear about the Twingy project, where there's digital twins for green hydrogen transition in steel industry. This is has 9 partners, runs from February 23 until July 27, and has a budget of 8.5 million, represented by Johannes Losacker in this case. Thank you very much for your availability. And the project Alchemia, this is data and decentralized artificial intelligence for a competitive and green European metallurgy industry. This is 10 partners running from September 22 to August 25 with a budget of 3.2 million. So these are the 3 projects that we're going to hear about and how they approach the issue of decarbonization, which we're all interested in. So yeah, thanks for joining us. By now we're quite, well, 2/3 of the participants registered, so there might still be some people dropping in. But for everybody who's been here from the beginning, thank you very much for joining and showing your interest. And I hope this is going to be a productive hour and a half, more or less. I'll try to do some timekeeping for the speakers, just so we have an averaged discussion there. And well, I welcome Celsa to introduce us quickly to their way of dealing with things.
Thank you, Ivo. So today I don't want to make any marketing presentation about Celsa. We recognize we are not Apple or Google, and for sure the steel industry, more or less, we have all similar innovation strategies. And this is why I think it's interesting to have this presentation today, because the idea is that we want to provide our views on how innovation can support the steel sector, not only to improve their impact into environment and society, but also to be more competitive, which is clearly important for survival. I hope that you are seeing my slides properly. Otherwise, please let me know. But first, to start, just a few words about what Celsa is. We are a European steel recycler with scrap processors, melt shops, rolling mills, and final transformation plants in Spain, UK, France, the Nordic countries, and France. And we produce around 6 million tons of long steel products for mainly the automotive sector and the construction sector. Other sectors are also very important as well, but these are the main markets. And we have an ambitious sustainability goal, which is to become net positive by 2050. This means embracing decarbonization and circularity. And in this slide, you see the strategical journey that we have defined before getting to this conclusion about the goals that we want to have as a company, our purpose, our mission, our vision. This is important because this is also the rationale behind our innovation strategy, because we don't innovate for the sake of innovation. No one should do it. We innovate because we have a mission or a vision, okay? And if we look at specifically the innovation roadmap of Celsa, we have 2 main goals, the zero emissions and the full circularity, very much aligned with the sustainability goals. If we come to zero emissions, we have defined 3 innovation programs that are aligned with the different scopes of the emission. So scope 1 is about decarbonizing our steelmaking process. In this sense, we work on unlocking technologies that would enable us to consume alternative fuels like biofuels or hydrogen. And you have Twingy as an example of it. Another one is to replace the use of anthracite by biochar or carbon capture and storage. If you look at scope 2, program 2 is related to optimizing our process in order to consume less energy or other other feedstock as well, which is in line with this other kind of scope of emissions. In this sense, artificial intelligence is critical, and today I will speak quite a lot about it. Well, not a lot because I don't have so much time, but most of my presentation. And then finally, scope 3 is rather about helping the value chain to decarbonize. For instance, helping our suppliers, lime suppliers, for instance, as an end user, testing the products that they are developing in processes that have a lower carbon footprint. I will focus on program number 2 today because I want to talk about digitalization rather than the other kind of technologies we could work on. And then just a few comments about circularity. This is important for us because we are a recycler, first of all, but also because something that is different between Celsa and other steel makers is that we are very much vertically integrated. So because we have these different 4 steps in the value chain, from scrap processing to final transformation plants, we can have a big impact when it comes to transitioning towards a more circular economy. And we have a lot of projects taking advantage of this situation. So we upcycle byproducts, not only from the steel making side, but also from scrap processing, which means upcycling aluminum, copper, zinc, plastics. Then we have new business models, for instance, having new scrap streams like photovoltaics in order to help in the recovery of these products, or new business models for steel products, which could be steel reuse, for instance. And finally, we also work on efficiency of non-material flows like water circularity or heat recovery. So that's the overview of the different programs that would bring us to the 2 main objectives we have. But of course, we don't need to forget of our 2 travel mates in the journey. So digitalization and people, they are obviously critical. People, because they are the core of any initiative and company. And in this sense, in order to empower them to make the most of them when it comes to improving the company in general, upskilling them, creating a culture of innovation so that they embrace the new technologies, and of course, protecting their safety is very important. But today I will focus on the other travel mate, which is digitalization, and what are the challenges we face there in this sense, and what are the opportunities it brings. So if we look at our process, that's important to understand our digitalization strategy, and I have already mentioned that. We cover these 4 steps of the value chain, and it allows us to be a critical agent to close the loop of 2 very important value chains, construction and automotive. You will see later why it's important. So we have categorized the challenges in digitalization in 3 categories: enablers, process revolution, and market revolutions. I will go through all of them, but just as a first hint, when it comes to process revolution, we work a lot with melt shops and rolling mills because they are the ones that emit the most, and therefore the ones that also consume the most. So simulating new situations in which we have new feedstocks or alternative fuels consumption, optimizing the process, and also guaranteeing flexibility and adaptation in front of market disturbances is very important, more than in the other sections, in the other plants. In the contrary, when it comes to disrupting the market, traceability is very important, and the impact of scrap processors and final transformation plants is much more important because they are the end-to-end part of our position in the value chain, and you will understand it better later. So starting now from the beginning, enablers of the digitalization for any company, but specifically for CELSA, what we have experienced in our digitalization journey is that data, this key enabler, is a tricky one. It's tricky to get the data we want, to select correctly the data that we need to extract, and also to store it in a way that later it's easy to get it and work on it. That's one thing. And then the other one is knowledge. In some cases, at the beginning, most of all, we thought that we had to have all knowledge in the company. So that if we work on predictive maintenance, we need to define ourselves what is the software that we need for predictive maintenance, pay someone to just deliver the software and use it. And it's not the way that it should work. We have learned by experience that knowledge doesn't need to be always inside the company. Collaboration makes things much better, much quicker, and with much more efficiency. And therefore, we have opened much more the doors to collaboration, as you see in the projects that we will be presenting today, in which data and knowledge have been key enablers and have been finally unlocked for the purpose of these three areas: simulation, optimization, and flexibility for our process. There was something written in the previous slide about managing expectations, and this is very much related to this slide. So when you are part of a very motivated team, like CELSA is, if you start defining an innovation digitalization strategy, you want to have the biggest impact possible, and you define very ambitious projects that motivate a lot everyone, but at the end you never finish. You get demotivated by your very high expectations, and this is something we don't want to repeat. So we have defined this very ambitious vision of having a digital twin of our process in terms of the melt shop and rolling mill, but in the very contrary, we have also defined very small and not so ambitious projects that would allow us to walk very slowly towards this aim of having digital twins. So we have some projects focusing on the scrapyard, others on the electrical furnace, others on ladle furnace, but each of them is answering very specific questions that will add into this digital twin. Okay, and some of them are also part of the projects that we will present today, which are Alchemia, Twingy, and Flex4Fact. If you look at it from the point of view of the three main opportunities that digitalization brings when it comes to process revolution, Alchemia represents optimization. Thanks to Alchemia, we expect to decrease by 5% the energy consumption in our factories. Twingy is an example of simulation. Thanks to Twingy, we expect to be able to understand very well what are the best blends that we can use in our reheating furnace when it comes to shifting from natural gas towards hydrogen. And finally, Flex4Fact allows us to be more flexible in terms of planning and reacting to the disruptances of the electricity market. And just to finish, I also mentioned market disruption. Why? Because when it comes to sustainability and to competitiveness, we need to work not only from the point of view of improving the way we work, so process revolution, as I mentioned, but also ensuring the competitiveness in the market. If the sustainable products are not more competitive in the market than non-sustainable products, it doesn't make any sense. So how to distinguish the more sustainable rebar in the market? Because green steel is not really green, right? So Of course, market needs to be defined by policies, by regulations, etc. But technology can also help. And this is why digital product passport and traceability is so important for us. So in a future, I hope, not in the long term, but soon future, we will have a webinar on that, on the different projects that we are developing in terms of enhancing traceability of the value chains and how this impacts the market for sustainable products. So just to finish, I would like to highlight the message today, which is that when we innovate for sustainable steel, we need to think about transforming production and market as well. But today, let's welcome the transformation of the production side. Thank you.
Thank you so much, Anna. That was a really nice presentation about the doings of Celsa, and I'm quite impressed that you're so on the forefront of, especially in the steel industry, of innovating and really working on making it more sustainable. And I'm really looking forward to hear the projects now, and I hope you are as well, to dive a little bit deeper into their different approaches and how this is supporting your innovation agenda. And so let's start with Flex Perfect. Matteo, the floor is yours.
Thank you very much, Ivo. I think you can see my screen now, right? Yes. So my name is Matteo Ganaboldo. I'm a researcher at the Technical University of Catalonia, made UPC. And I first want to thank Irene for organizing such an important event at the World Celsa Group for this. What I will present is the work that we have done within Flex Perfect, focusing on the optimal planning of the electrical arc furnaces, including the energy vector explicitly in the planning, and to generate flexibility offers for the market. Okay, this is the results of a work that has been done along more than 2 years by a pretty big group of colleagues, okay, part of 2 different research groups within the university. One is called SITSEA, and the other one is called DOPS. Okay, so the project was already introduced by Ivo and also Anna. Here, basically, just to remind the main scope of the whole project is to develop an end-to-end ecosystem, okay, that takes a modular approach to provide flexibility services to the market and to introduce renewable integration in the process. Okay, so this is, as I say, is a modular approach. So this is done by different layers. We have digital twins. We have the renewable energy integration. We have the flexible scheduling and planning part, and then the industrial cluster flexibility platform for the relation with the market. Okay, we will talk a bit about flexibility later. Okay, so this project was focused on 5 industrial settings, but today we will clearly just focus on Celsa and basically on the algorithm we developed for the scheduling and planning of operation. Okay, so we started from analyzing, if we look at the whole process, this is the factory of Celsa in Barcelona, okay, that I've already shown a bit. Basically, the main operation can be divided into a melt shop, where we have different furnaces that melt the scrap, and then the rolling mill. Okay, so the numbers that we see here in this picture are basically the average electric consumption of the different process. And it is pretty evident that the process that consumes the most is the electric arc furnace. Okay, actually there are 2 furnaces with an average consumption of 70 megawatt each. So it's 140, 150 megawatt if we sum both of them. And analyzing those processes, we see that there is certain flexibility, okay, because those furnaces can work in 2 power configuration, low and high power, and that these configuration changes can be done pretty easily by the operator and workers of the industry. Okay, so we started basically analyzing then the real consumption of those furnaces. And this is as part of a study that was done by our colleagues from ITA, the Technical Institute of Aragon. So they analyzed the consumption of almost 2 years of data And what we see here is the hourly average electric consumption in each of these hours, okay, for the two furnaces. So if we mix these with the also knowing the power mode that was used in each moment, it was clearly visible that there are these two modes, okay, the low power mode and the high power mode. And it has been possible then to characterize which is the average consumption of both of those configuration. And clearly higher is the power consumption, higher is the melting rate. Okay, so the melting of the here is visualizing ton per hour or casting per hour, considering that one casting is 148 tons. Okay, starting from that, we developed a mathematical model, an algorithm that basically with the aim of optimizing the operation of those two electric arc furnaces that, as we say, each has two operation modes with different melting speeds, knowing that this melting is organized in casting and that the planning horizon is 15 days. So in parallel, what we develop is also an electricity price forecast algorithm in order to estimate the price for the next 15 days. So what we need to define is basically the hourly power configuration during production, and then if we need to stop a furnace, with the objective of minimizing the operation cost, that in this case takes into account both electricity and the material. With all the different constraints that resulted from talking with the industry and trying to understand the different limitations and things to take into account. So the demand of casting has to clearly be fulfilled. There are some time slots that need to be saved for maintenance and all the other operational constraints, like, for example, the fact that it needs to stay in a certain operation mode for a certain time. And also, we want to fulfill the service that Celsa is currently providing to the grid, so that it needs to assure a minimum consumption during certain hours. Now we can see the results, okay, in a 15-day period between the 1st and the 15th of October 2023. And what we see here is basically the results of this baseline of this optimization model, where we see in each hour for furnace 1 and furnace 2, which is the operation that need to be taken. Okay, so in green we see the high power mode, in blue the low power mode, and in yellow we see if there are maintenance, and in red the stops. Okay, so what we have done is to compare the results that we have obtained by our model with the real production followed by Celsa, and clearly maintaining that the production is clearly the same, no, because if not, it doesn't make sense. So if we focus on those 3 days, okay, we have what we see here in orange is the electric consumption of the plants followed by the industry, and in blue we have the consumption of the optimized plants that we obtain. On the other side, in gray, what we see is the electricity price, the hourly electricity price of the spot market forecast. Okay, as we see, the optimized plant tends to clearly consume more when we have low electricity price, and these lead to a certain saving in money in these 15 days planning. Okay, now what you may want to ask is where is the decarbonization here? Okay, and here I try to explain the answer. So what we show here in blue is basically the electricity prices, the hourly electricity prices in 2023 in Spain, and they are plotted against, in each hour, depending on the electricity mix, we have certain CO2 emission factors, so kilograms of CO2 for each megawatt hour that is produced. Okay, clearly, as more renewables enters in the energy mix, the energy price goes down, okay, because the fuel is free in this case. And on the other side, yes, also the CO2 emission of the energy mix decreases. Okay, that's what we've seen here. And in other there is this direct correlation between the spot market prices and the equivalent CO2 emissions. So basically, if we go back to the previous results, here is the same chart. We just added in black the CO2 emission factor that, as you see, is following pretty much the price. Okay, it is in gray. So even if the CO2 is not explicitly included in the model, we see a significant reduction in the CO2 emissions from the grid consumption. Okay, in this case, around 400 tons. It is around 5.5% with respect to the industry plan. The next step is the generation of flexibility offers. So here, before talking about that, I want to introduce what does we mean flexibility in power systems. So it's basically the ability of the power system operator, generation, storage asset to change their routine operation for a limited duration, responding to an external request, okay, in order to maintain a constant balance between generation and production and consumption. So if we look at this chart, okay, if we focus on the left part, we see that traditionally this flexibility comes from the supply side. Okay, if we have thermal power plants, they can increase or decrease their production in order to adapt to the consumption. Okay, are flexible power plant. But if we move on the right axis to the x-axis to the right, then if we increase the level of renewables such as wind and solar, those generation does not have any flexibility. So the supply side flexibility is decreasing, while on the other side, the total requested flexibility by the system is maintained constant or even can increase. Okay, so this results in a flexibility gap that can be filled from by flexibility from other sources. Okay, an example can be our grid side. So it means generating, enlarging the grid or improving the high voltage connection between countries. Storage side, but it's not that easy when we talk about this amount of electricity. And finally, we have the demand side. Okay, it becomes very attractive because it doesn't require much infrastructure and is especially attractive for energy-intensive processes like the steel industry. Okay, so how this industry can enter can provide this demand-side flexibility is by entering, for example, in the flexibility market, such as ancillary services market. And in Spain, I will not enter in the market of electricity because it's a huge stuff, but just to mention a couple of markets that are very interesting for the steel industry or for CELSA can be the tertiary reserve or replacement reserve, where basically there are daily auctions of a minimum bid of 1 megawatt hour and offer duration between 15 minutes and 2 hours, having a notification time of 15 to 30 minutes before activation. Okay, so basically what's, to go back to the example, okay, what's here we see the baseline consumption, so the optimal plan, or the plan the industry is planning to follow for the next day. In this case, it's between 6 in the morning to 6 in the morning of the next day. And so we adapted the algorithm in order to generate flexibility offers. What does this mean? For example, our result of the algorithm will be to say, okay, we can, at this time, at 15 hours, we can decide to stop the machines, both furnaces, for 2 hours, as we say, that's the maximum time, and then to recover this production before the end of the day afterward. Okay, so basically, we are offering, in this case, it's 146 megawatt per 2 hours at a certain price per megawatt hour. Okay, I will try to quantify which is the cost of making this offer. As you see, it's a pretty high cost, very difficult to get accepted by the electric market in this case. So another option that can also say it's Okay, we don't have to stop the furnaces where we get some material and energy loss. We can also just say to change the power mode of both furnaces at the same time. And so in this case, the bid offer is lower, is 38 megawatt for 2 hours, but the price is much lower, so a much higher possibility of getting accepted. Okay, that was basically it, what I wanted to explain, just to give an idea of the current status where we are. Basically, the algorithm for this baseline or the optimized plan and for generating those offers have been already developed and tested. And what we are working on now is the software interface and connection that are actually by development by WePlus, that is also developing the energy flexibility production scheduling platform where this algorithm will run, and with all the user interface nice as much as possible. And this is the platform that will then interact with the industrial cluster flexibility platform, that is the one related with the relationship with the market, and for sending those offers, aggregating the offers from different industry and sending them to the market. So thank you very much for your attention, and looking forward for any question or any doubt you might have.
Thank you so much for this enlightening presentation. I think it became really clear that flexibility and the understanding of energy usage leading to this flexibility really offers the chance to adjust your production in a way that saves energy or no, redistributes energy to save costs and CO2 emissions. So I would ask if there's a pressing question right now from somebody in the audience. Otherwise, think about this. This is the first approach. Think about it, write it down, and yeah, maybe there will be some discussion in the Q&A afterwards. Yeah, without any further ado, I think we move over to another way of decarbonization strategy with Johannes Losacker. And yeah, the floor is yours.
Yeah, thank you very much for the kind introduction. I guess you can see my screen, just let me know otherwise. So I'm going to present the project called TWINGY, which is short for Digital Twins for Green Hydrogen Transition in Steel Industry. I'm Johannes Losacker. I'm a PhD student. I'm in my second year at RWTH Aachen University, and I'm at the Department for Industrial Furnaces and Heat Engineering. So this time it's not about the electric arc furnace, but rather about the reheating process of steel. So this is taking place at the hot rolling mill. Here in this picture, you really nice see some heated billet. It's got heated in the walking beam furnace in Celsa 3 that you see in the background. So here we did some special measurements. That's why it's about to be removed by a crane. Usually this hot reheated billet will just stay at the roller table and go straight to the hot rolling mill. And there it's getting its final product shape. So this reheating process is taking place at Celsa 3 in a so-called walking beam furnace. So there's several beams, stationary and walking ones in this furnace, and they do kind of like a stepping pattern to move the billets through the furnace. So indicated by this black arrow down here, you see the billets are entering the furnace chamber, which is indicated by this yellowish in this figure here, which shows the furnace from the top view. So the cold steel billet is entering the furnace down here, and then it's stepping through the process, going upwards in this figure, and then leaving the process after about 3 hours, then being hot and ready to be hot rolled. So this furnace is operated by burners. You see them depicted here by the red arrows. It's 24 burners in total, 12 to the right, 12 to the left side. And then these burners burn into the combustion chamber, produce flue gases that are hot, transfer their heat to the billet, and then the flue gases are leaving this combustion chamber down here to the central recuperator, where the off gases that are still hot preheat the combustion air, so that's nice for some energy efficiency increase there, and then the cooled flue gases are leaving the system via the exhaust through the chimney. So this process is responsible for over 50% of the CO2 emissions at the Celsa 3 site. This is regarding to the scope 1 CO2 emissions, so the CO2 emissions that actually are emitted on site. So you see here in this diagram, it's more or less a rough estimation. I got some figures from Celsa Sustainability Report from 2023. So this reheating process really has a great share of scope 1 CO2 emissions. And this is due to the fact that this furnace is operated on natural gas only. So to give you some basic figures of the furnace and the process, it has a nominal production rate of 180 tons of steel reheated per hour. It usually runs a bit lower, like something about 100 tons per hour. And in this case, steel billets are entering the furnace at about ambient temperature, about 20 degrees Celsius usually, but sometimes as these billets are coming straight from the caster, they might have not been cooled down entirely, so they might also have temperatures like 300 or up to 400 degrees Celsius. They are getting loaded into the furnace and then getting heated up to something like 1,200, 1,220 degrees Celsius for hot rolling. This is done with an installed power of 79 megawatts of natural gas. And this results in the end in specific CO2 emissions of about 60 kilograms per ton of steel that's being reheated. So the scope of Twingy is to decarbonize, at least partially decarbonize, this reheating process. And we follow two major pathways to do that. The first and arguably most important one to reduce emissions is the introduction of hydrogen and also oxy-fuel. So we are retrofitting the furnace in parts at least by newly developed burners that are capable of firing hydrogen. And as most of you might know, firing hydrogen doesn't produce any CO2. And so that's our way to go. So here again on the right side, you see the top view of the furnace. And now some of these burners are marked in green. These 4 green arrows are actually representing 8 burners because they are in 2 rows, 1 top row, 1 bottom row. So out of 24 burners, 8 of them are getting retrofitted by these new fuel flexible burners. These burners have been developed of our project partner, FIFS, who happens to be the furnace manufacturer as well. So they really know their furnace and how to integrate their new burners. So really within this project, they developed the new burners. Fuel flexible means in a sense that they are able to operate on hydrogen and natural gas both, and actually any blend in between these two. So in the heating zone, which is one of 3 furnace zones consisting of 8 burners, these are getting retrofitted in the furnace, and this heating zone is actually the one with the greatest share of energy contribution. So it's quite reasonable what we are retrofitting here that is able to be operated on hydrogen then later on. Of course, we have to be able to supply the hydrogen to the furnace, which is actually a major challenge because we don't have a grid like we do have for natural gas. So our project partner Nippon Gases is taking care of the infrastructure that is required to get the hydrogen to the furnace, which is done within this project via trucks. At least 2 trucks are able to connect to the piping system that is then introduced by Nippon Gases to the furnace. And then we are able to operate the furnace, at least for a couple of hours for our test trials on hydrogen. Moreover, Nippon Gases is introducing 2 additional burners. And one special thing about these burners is that they are operated on oxy-fuel. They are introduced at the back wall of the furnace. So right now there's no burners there. These are just additional for, let's say, research purpose. And the nice thing, besides the fuel flexibility again here, is that they use oxy-fuel. So they use oxygen, pure oxygen, instead of air for combustion, which essentially makes the process more efficient because you don't have to heat up all the nitrogen that's contained in the air. So the flame the combustion itself, the flue gases are actually gaining temperature from that, and this in turn promotes the heat transfer to the product. The only drawback, of course, is that oxygen has some certain price, while air is basically for free. So this is the one pathway, the actual retrofit of this furnace. And of course, we want to answer some questions. What are the consequences of the fuel switch going towards hydrogen, at least partly towards hydrogen? So we want to see how's the process efficiency evolving. One important question is about scale formation. So for any of you who might not know, in this reheating process, the steel product is partly oxidized. So that's actually steel mass that we are losing within the process. And this we don't exactly know to which extent right now, but that's why we're investigating it, how the altered furnace atmosphere by the introduction of hydrogen, so fewer CO2 content, higher water vapor content, will affect the scale formation. Then another material that's in contact with the furnace atmosphere is the refractory. So that's like the lining at the inner furnace wall that's protecting the walls from the heat. So we expect some interdependency with the flue gas atmosphere there as well. Then we have one important point, which is pollutant emissions. Mainly we focus on NOx emissions because the higher flame temperatures of hydrogen flames make it a bit uncertain how these emissions will evolve. They will get higher, lower, whatever this is to be investigated within the project. And then in the end, we have kind of like the quality of our process. So in the end, we want to reheat the steel billets. So the temperature distribution within the billet is what we're aiming for. And as the heat transfer due to the fuel switch might change, we also going to investigate the temperature distribution in the billets, how we might have to change furnace control or some other parameters to still remain at least the same quality of heating of the steel billets. So that was the first pathway, so to speak, the actual retrofitting of the furnace. The second aspect we are focusing on is the use of digital tools. So here you see some nice CFD picture standing for that. So I want to start by motivating the use of digital tools a bit by showing you what kind of data is generated at this furnace. Because actually, even though this furnace is operating for 15 years now, it's equipped with quite a lot of sensors. So for each and every single burner, we have the natural gas flows, for instance, recorded all the time, together with all the air flows, what's going into our system. We also have a bunch of thermocouples that's giving us the gas furnace temperatures within the furnace chamber in the different heating zones, and also in the off-gas channel, the off-gas recuperator. And additionally, we performed some measurements. We've been there at the site for about a week. We recorded some off-gas, flue gas compositions at different accesses into the furnace chamber and also at the chimney. Here I brought some picture with a quite nice view from up the chimney over Castelbisbal. And within this week of our reference trials, where the furnace was operated on the usual natural gas fuel, we also did some investigation of the steel temperature. So what we always know is what kind of temperature has the steel billet when it enters the process and when it leaves the process towards the rolling mill. But within this reference trials, we also performed a so-called instrumented billet trial. So this is the picture I was showing you earlier. It shows a billet being removed from the process, and you see something attached here. That's a data logger that's connected to a couple of, I believe it was 25 thermocouples that are placed at different sections along the billet and then at different depth. So in the end, we have some transient temperature profile, and now know actually how the temperature distribution within the billet is evolving throughout this process. So then we, of course, have all kinds of data that is characterizing the movement of the billet through the process. We know about the water cooling, how much energy is extracted from the furnace by the flow of water, inlet and outlet temperatures, and so on, a whole lot of other signals. So my point here is actually only that we have lots of data and lots of information of the operating conditions of this furnace. So we know a lot of things, but we don't know everything, for instance, when it's about the details of the flames. And here, some digital tools as CFD, namely, can help us. So on the left side, you see some high-fidelity large eddy simulations that have been performed by our project partners from the Barcelona Supercomputing Center. So this is the newly developed fuel-flexible burner developed by Fives and their combustion test chamber here. And you see this is a highly resoluted simulation where actually lots of the turbulence is resolved. So you can gain a lot of insights about the flame characteristics, also pollutant formation and heat transfer from these kind of simulations. The only drawback is that they are quite expensive. So what we do within the project is we derive some cheaper simulations that are performed in the RANS framework. So that's done at our university. So here you basically see the same furnace chamber, just temperature field in this case is more smeared out. This is basically time averaged. And the thing with these simulations is that they are that cheap that you can easily, or not easily, but you can run them for an entire furnace, and then you can get way deeper insights about temperature distribution, species compositions within the furnace, and the heat transfer towards the product in the end. So combining these kinds of informations, our partners from the Barcelona Supercomputing Center add everything up and build a digital twin out of this data. So we have chemical reactor networks. That's some 0D simulations that they perform. Then they do machine learning on all this data I showed you before. That's generated through long times of operation at this furnace. So they basically do like time series predictions and explore various models for that. And then we have the insights we gained from the CFD of single burners, the entire furnace, and in combination, all this gives us a lot of insights, and that's what one may call a digital twin in the end. And then one second, so to speak, more classical approach of a digital twin or a process model is developed by another project partner, Swerim in this case, and they are actually doing some finite element analysis of the system. So they do a discretization and they derive this model from first order physical principles. So they calculate heat flows, radiation from the flame, from walls, gas radiation, convection, and so on. So this is like the classical approach. And in the end, one aim of this project is to compare these two approaches to a digital twin. And of course, we also want to answer some questions by the use of these digital twins. And we also want to know which method is preferred to answer which question. So here again, it's about how is the heat transfer, how is the fuel switch influencing the heat transfer in our system? What's the general response of the furnace if we change burner states or the operating conditions? And then in the end, if we have a model that properly describes the whole process, we want to be able to get information out of it about what would be the most economical operating strategy, which kind of blend of hydrogen or natural gas, to which extent should we use oxygen as the oxidizer. And then in the end, we could also use these tools to assess the most ecological operating strategy for the furnace. So this project progressed for almost 2 years now. We are in month 22 out of 54. So we already completed some actions, which first of all would be the development of the fuel flexible burners. This is done already. So these burners are now getting manufactured. And then we performed some reference trials where we got deep insights into the process. And we did some lab trials about the materials to see how the interaction with the altered flue gas conditions will be. So this is referring to the refractory material and the steel samples. We also placed some of these samples into the furnace, but the thing is we can access it just during maintenance. So there are some samples placed in the furnace right now that we will be able to analyze later on. So the next major actions will be the actual retrofit of the newly developed burners and the oxy-fuel burners into the furnace. Then it's time to actually operate the furnace on hydrogen. This will probably last for a couple of hours when we have 2 trucks of hydrogen available. So we hope we get some nice data out of these trials. And then in the end, in parallel, we are about to develop and in the end compare the digital twin approaches, yes, to have some conclusions for which kind of question, which modeling procedure is preferred. And that's in a nutshell the Twingy project. Thank you for your attention.
Thank you very much, Johannes. That was really technical. I see we really went deep into the workings of the furnace and the engineering parts of the project. But thank you very much. This seems to be really integrated into the manufacturing hardware of Celsa as well in this case, and already changing the way the steel is produced there. So thanks very much. Is there any direct comment or question in the audience right now that's pressing on your lips? I would hate to take away. Yeah, Ingeborg? Hello.
Hello, my name is Ingeborg. I'm a research scientist at Sintef Energy. First of all, thanks, Johannes, for very, very thorough presentation. It's really, really nice to see. I was wondering for the hydrogen supplies, have you considered including pipeline supply?
I'm afraid I didn't get the last part of the question.
I was wondering if you have considered including pipeline supply of hydrogen.
Not as far as I know. As far as I know, we rely only on trucks to supply the hydrogen for our test trials.
Mm-hmm.
Maybe Celsa has some more insights about whether there's any pipeline for hydrogen in the near future.
Exactly. We are monitoring the situation of the hydrogen market in Europe in general, in the countries where we have industries, but specifically for Spain, we are part of different networks in different regions, and there is no plan right now in the short term to have any electrolyzer close to our factory, so it's not possible to get this hydrogen. However, because different industries in the region are developing technologies to consume hydrogen, we hope that there will be some more motivations to install it. We don't know. That's why we are in collaboration with Nippon Gases, so that they can provide the trucks for the trials. And in the future, we hope that the market will be better for hydrogen consumption.
Thanks. We'll have one more question before we proceed with Halvor.
Oh, thank you. I'm also from Sintef Energy, a colleague of Ingeborg. Thanks a lot for the presentation, Johannes. I was wondering what is the hydrogen content? It was a mix with hydrogen and natural gas in these burners. Can they go all the way to 100% hydrogen?
Yes, they do. And that's actually what's planned for our test trails, at least for a couple of hours, as long as the hydrogen supply is.
Okay, Yeah, thank you.
Just a
Yes,
very
Ingeborg.
quick comment
go.
or question
Very good.
clarification to that. So that would be 100% in the 8 out of the 24 burners.
Yes, exactly.
Is that correct? Yeah.
Yes, and one thing maybe worth mentioning is that these burners are operated in like a binary mode. They are either on or off. And in the usual furnace operation, they are never always on this at the same time. It's just a fraction of the burners firing at once.
Okay, thank
Okay.
you.
I see there's some joint interest and understanding regarding this. That's very nice. But to give the same share also to Alchemia, I would like to introduce Aitor and Stefano, I don't know, to the stage. So please use your time, and I'm interested to hear your approach to the solution.
Hi everyone, I'm Stefano Vettori from Scuola Superiore di Sastana. I'm assistant professor, and I'm going to present some results and some ideas that we are applying in this project that is called Alchemia, which objective is not to transform the scrap in gold, but something similar, let's say. The idea is to exploit, in fact, data. We have a lot of data. We would like to exploit in a decentralized way artificial intelligence for enhance the production of the steel from the EAF-based steel production. So the idea of the project is to optimize the recipe of the steel using some scraps that are available in the scrapyard, and obviously ferroalloys for doing some refinement of the steel composition. The idea is to provide a set of tools, a lot of based on artificial intelligence methodologies for starting from the scrap purchasing to, let's say, the final evaluation of the product quality at the end of the ladle furnace. In the middle, we have several processes that we can optimize or, let's say, monitor in a more intelligent way. So from the scrap purchasing to the scrap processing, where we can assess the quality of the scraps once processed. Then we can do an intelligent inventory of the scraps and optimize the recipe through an intelligent, let's say, an adapted recipe that starts from, for example, the characterization of the material feedstock. So in this case, the scraps. Then we have the EAF process where we can optimize several things such as carbon usage or the energy, all the energy carriers. And finally, the last step is to optimize the refinement of the steel, as I said before. So by adding, for example, the ferroalloys in the ladle furnace. And in fact, the ladle furnace is let's say, the objective of this presentation. The objective of the project actually are the development of a decision support system for optimizing, in fact, the recipe for the steel production. In this decision support system, the operators can, for example, set a set of objectives that they would like to minimize or maximize, for example. They can also set the parameters for the optimization, but set also, for example, some characteristics, in this case, in the case of the ladle furnace for the ferroalloys in terms of chemical contents, and also prices of materials and also the energy carriers. And thanks to these data entries and a set of models and optimization tools that are integrated in this decision support system, the decision support system deliver to process operator, a plant manager, a set of results that are, for example, an optimized recipe for the ferroalloys addition in the case of the ladle furnace, also an optimized the consumption of energy and argon for the steering of the steel. And finally, also show what will be the characteristic of the final steel at the end of the ladle furnace process in terms, for example, of final chemical composition of the steel, if it meets the target composition, and the final steel temperature. And also, the idea is to also show also the economic and environmental impacts of each specific heat. For doing so, the decision support system integrates several components, starting obviously from graphical user interfaces, where operators, in fact, can set a set of parameters and then visualize the results, an optimization framework, a life cycle assessment framework, and a set of machine learning-based models. Going into details, basically the decision support system starts from a set of measures such as the temperature during the tapping of the IF, the temperature of the steel, and the composition, let's say the starting initial composition of the steel before the ladle furnace process. Then, thanks to the optimization framework, we can formulate an optimization problem where, for example, we can insert a set of constraints that describes, for example, the process behavior, in this case, the ladle furnace, but also the limits of all the manipulable variables in terms, for example, energy usage and the types of operation and so on. And finally, also insert a set of costs that describes the balance, let's say, in terms of economic impact that takes into account the energy consumption, the argon consumption, but also the ferroalloys usage, and also the costs related to the environmental impact. The interesting idea in this project is that we exploit and we leverage also a quite powerful tool that is the LCA, the life cycle assessment methodology, that allows us to calculate the environmental impact, to assess the environmental impact for several categories. In particular, for an IF-based steel-making process, the most relevant categories are, in this case, the climate change, the acidification, the eutrophication in terms of fresh water, the photochemical ozone formation, and ozone depletion. But we can calculate several categories. This calculation, basically, this is a calculation of a set of environmental impacts that are numerical values, are calculated starting from the usage in terms of materials, but also energy and water and so on. As I said before, the decision support system integrates a set of models, in this case, that describes the ladle furnace behavior, and exploit neural network for forecasting the final chemical composition and the final chemical temperature. These models are trained through real data of the plant, of the specific local plant where we deploy the decision support system. But the interesting fact of this project is that we are using and exploiting the federated learning that creates a sort of global model that, let's say, integrate all the knowledge of several plants that collaborates to create let's say, an enhanced global model. And this will be explained better by Aitor after my part of presentation. These models exploit, obviously, a set of inputs that are, for example, the chemical composition during the tapping in the IF, so the chemical composition of the steel, the steel temperature, ferroalloys addition, obviously, the argon consumption for steering, the electrical energy consumption, and also the weight of the scraps loaded in the electrical furnace. And this is an example of how, let's say, in a test set, these models works. These models exploit a quite simple architecture that is based on neural networks that are the feed-forward neural network, are trained with about 2,000 of it, but thanks to the exploitation of the federated learning approach, this model will be enhanced through a lot of it from all the plants participant to the project, basically, that exploit obviously a little furnace. And here we see some results. We see that the models these are results on the test set. So data that are not used for the training, but are only for the evaluation of the model. And here we see that the models has very high accuracy, and also in terms of R-square, and also that let's say that somehow gives the information of the quality, of the precision of the model, but also in terms of the percentage errors that are quite small. And then I leave the floor to Aitor. They will explain more in details the architecture and all these things. If you would like to share the screen, I leave you also the.
Okay, I will do it shortly. Okay, we were on here. On here. Okay, so if we take this information that was presented by my colleague Stefano, the idea of having only a single plant working on forecasting and providing these improvements in terms of artificial intelligence and digitalization perspective, we can encounter the way to provide the rest of participants, the rest of industry, with a way to work collaboratively so that they can create what it is called a global model. For such purpose, in Alchemia, we are working in federated learning principles. And as an introduction, federated learning is basically a way to extend machine learning approach where the models are trained collaboratively across decentralized devices. Following this, we ensure that we keep the data and the content private for the rest of the industries, and we only provide, in terms of exchangeable information encrypted, the models so that people can create this model at the end that will be consumed by all as a positive way. If we see it as an architecture, we can imagine several plants that they don't want to share the data with each other. They could come from different companies or from the same company, but for strategical purposes, they don't want to share the data, so that they provide this data to make the local models that were presented before as an example. And these models are encrypted so that they are preserving the privacy of the different companies. We can imagine this as a splitted companies, decentralized and distributed around different places. And at the end, they provide those encrypted models into a single one, splitting it into a so-called clients, and then into a centralized server. This centralized server aggregates the information that comes from the different plants, and this information is sufficient to provide what it is called a global model that it is exposed to all the participants so that they can use this data having a better performance model than the one that they have locally. This model comes again to the clients so that if they has any changes in terms of data, or they would like to change something locally, this can improve the global model as well by working in a feedback way. Then our framework is aimed to provide a modular tool that allows us as a consortium or as a framework provider a way to implement these federated learning pipelines in a customizable way. This framework ensures the data privacy, as previously commented, by sharing only the model updates, not the data of the companies or the industries between the devices, safeguarding the sensitive information that don't want to be shared with each other. It supports the seamless integration across the distributed infrastructure. It comes from wherever independently and then aggregated into a single centralized point. And then it implements the governance mechanisms so that we can assign roles of or control access in enhancing the security when gathering these global models. And a short hands-on of how this is easily applied in a modular way is that we only need to have available a cluster with dependencies of Docker and kubectl installed, only for files, and then applying the deployment, we are able to deploy the federated learning framework both on the client and on the server, and start working, improving this global and creating this global model. Apart from that, we are focusing in machine learning operation as well. As a short introduction, for those who doesn't know what it is, machine learning operation is a set of best practices that unifies machine learning system development and deployment so that it extends the capabilities of the well-known DevOps. It is applied and tailored specifically for machine learning principles. The benefits of using MLOps inside this kind of projects is to accelerate the model development and deployment cycles, to improve the model accuracy, reliability, and compliance so that it is working continuously using SCI and CD techniques, and then to reduce the operational costs through the automation of these tasks. And applying this directly into the Alchemia solution as a whole, what we can see on here is the architectural design, the high-level design of the different components that we encounter. And this can be represented as a set of plants or different industry plants that will represent the so-called clients from before. Then we can gather the data from the local systems. It is extracted, transformed, and loaded into DCTL pipeline. Then we create the training pipeline, providing those machine learning models mentioned before by Stefano. And then using these privacy preserving techniques, they are aggregated into the central server, which is the right side of this structure. And then it is exposed through the inference pipeline, and using the monitoring and control component that we can see on here, we provide with this graphical user interface that were as well presented by my colleague Stefano. And then going through the conclusions of this project, we split this into three main pillars. The first one are the main outcomes in terms of technologies that we have, which are the federated learning approach, continual learning, so that we can monitor and continuously improve those models, the explainable artificial intelligence, and as well to present and provide people with these global models through the AI4U platform. In terms of optimization framework, we have the tools, the targets, and the results so that we can be able to get those KPIs that we have aligned with this decarbonization way to work. And especially for the CELSA use case, we have electric arc furnace steel making that we are aiming and going to get around 5% of reduction in terms of CO2 emissions. Apart from that, we have as well other pilot to be commented, which is Funderia di Torbole, that can join as well as an extra company to provide with their data so that they work inside this federated learning framework as a whole inside this fleet. And then just to mention that this design is aligned with the human-centric focus. It is compliance with the indications from Trustworthy AI from the European Commission, and we develop different development strategies, such as 3 workshops and having 200 workers involved in these pilots, focusing on the human-centered design. And that was all from our side. Here is our communication channels. You can contact with us or with the project if you have further questions. Thank you all.
Thank you so much. Also from that side, so there's I would say Celsa is in good hands with a lot of innovative ideas on how to support the transition for greener steel production. I mean, personally, I'm really impressed with all these solutions and work that's been done in there. Yeah, I was giving it back to the audience. If there's any question you have for the speakers or to Celsa, to Irene, to Anna, Johannes, Matteo, Stefano, or Ayrton, or anybody else? Very well. I mean, I also thought it was explained exceptionally well, all the concepts, so it leaves no questions open. Everybody knows what you're doing. But yeah, I mean, you've seen some of the context points. We, as you might have seen, we recorded the session as well, so there will be a follow-up email, and we will forward the communication channels of the speakers and the present presenters to the audience, if all you don't mind. But so if you have any topic-specific questions or you want to interchange for new project ideas, I think they're all, as we are all in this European ecosystem, all very open to collaboration and further project ideas. And I think if this leads to some bilateral communication afterwards, that's also fine. So if there's no questions in the audience, I would give the chance to Celsa, to Anna, or Irene maybe again, or to some of the speakers if you wanted to comment on one or so idea of the other projects, or if you want to put in any finalizing words there from Anna or Irene maybe.
So I will take the chance. I will take the invitation that you have launched to collaborate in future projects. And of course, we're very open to it. I think we are very clear in the sense that in terms of digitalization, our interests are always regarding simulation of what would happen if we use alternative fuels or alternative feedstock or variable feedstocks, flexibility in order to adapt to the very variable fuels, feedstocks, prices, etc. And finally, process optimization. So anyone that would like to make an Alchemia phase 2, Twingy phase 2, or Flex for Fact phase 2, please contact us. Well, and the ones that are working in Alchemia, Flex for Fact, and Twingy, there's still a lot to do. Huh? So let's focus as well on what we are already doing.
We're still in the process. Well, perfect. Thank you very much. Yeah, so that leaves nothing for me then to conclude the presentations, I think. It's been highly enlightening. I mean, for me, I'm coming from the Flex for Fact project, where I'm involved in that part. But nevertheless, it was nice to hear it explained in that way again. And thanks to the other projects as well to give an idea of how you're working. I hope you could take some information home with you, depending on your industry or type of work you do, coming from research or industry or steel industry or data industry. I hope this was enlightening to you as well. I hope you enjoyed the presentation. So thanks again to the presenters and to Irene for organizing this, and to Anna for representing CELSA in this case. And I wish you a pleasant evening. And well, you hear from us, and I hope this was worth your time. So thank you very much for listening in, and we'll see you next time.
Thank you very much.
Thank you, Ivo, for the moderation.
Bye. Thank
Have a
you.
good
Thank
day.
you all.
Thank you.
Bye.
Bye.
Thank you. Bye. No.
Bye.
Bye bye.
Hasta luego.